Okay, we are recording. Today we're starting our study of thermodynamics, and this is basically the study of things that change as a result of temperature changes, although in thermodynamics we also sometimes study the states of things as they remain at a constant temperature. But loosely, it's the study of things that change when temperature changes. And one of the first things that we need to get out of the way is talking about temperature scales, which is probably review for many of you. We're not even going to touch the Fahrenheit temperature scale in here. There's a little tiny chunk in the textbook that gives you the formulas for converting from Fahrenheit to Celsius and vice versa. But I'm just not going to deal with that at all. So the two temperature scales we're going to care about are the Celsius temperature scale. So try to hang on to my pen, and the Kelvin temperature scale. There's an experiment that we were able to do when I was at the University of Minnesota that let you do some experiments with, we had some bulbs that they looked like the old style of float that you'd see in the back of a toilet. They were made in kind of a copper bulb or something like that. And I've got some in the classroom. And we'd look at how when you change the temperature of the bulb by maybe immersing it in ice water or immersing it in boiling water or something like that, you'd see the pressure change. And we do experiments like that. But for now, we're just going to talk about a few things that might happen with familiar stuff. Water boils, water freezes. And when I say water boils and water freezes, I mean at 1 atmosphere of pressure. I don't know if anyone's ever experienced traveling to some place that's very high altitude. Water boils at a lower temperature under those circumstances, and noodles that might have cooked in 10 minutes down at sea level or at a low elevation will take a lot longer than 10 minutes to cook when you're at a higher elevation, because the water just isn't as high a temperature. Used to be on recipe boxes, like for cake mixes and things, they'd have different baking times for things that were at high elevation. I haven't cooked a cake like that in a long time, so I don't know. We tend to make ours from scratch. Anyway, water freezes, various things happen. Well, on the Celsius scale, water boils at 100 degrees Celsius. Water freezes at 0 degrees Celsius. And another change that might happen is that an ideal gas, and we'll do some studies of ideal gases a little bit later in this unit, exerts no pressure. Okay, and that happens at minus 273 degrees Celsius. Now, there's something that's tagged onto here, 0.15 a lot of times, but to 3 significant figures, this will be good enough. In that experiment that we used to be able to do at the University of Minnesota, one of the things that we could immerse the glass bulb in was liquid nitrogen. And I guess we could buy liquid nitrogen here in town if we wanted to. But in fact, I think I remember the chemistry club a few years ago making ice cream with liquid nitrogen. But anyway, you could have an intermediate temperature here with liquid nitrogen. Something you find is that as the temperature decreases, the pressure exerted by a gas would decrease linearly. And so if you made a graph of the pressure exerted by the gas as a function of temperature, you'd find out that it was one amount when your temperature was 100 degrees Celsius, and it would drop by some amount when you were at 0 degrees Celsius, and then whatever the temperature of liquid nitrogen was, it would do something similar, but it would follow a kind of linear pattern for a while. Although with some gases, like say if you had ordinary air in the thing, at some point, instead of following this linear thing, it would just plummet to something, and then it would go at a different angle for a while, and then it would plummet again, if you could do that. Well, what's happening in that case is that some of the gas in your bulb is changing from a gas into a liquid, and that liquid isn't going to exert pressure anymore. So things would go crazy. But if you extended this straight line back, and I kind of messed up my thing here, but you get to a point at about minus 273 degrees Celsius where the gas no longer exerted any pressure if it was an ideal gas. And there's a kind of myth that's grown up around this particular temperature. It's referred to as absolute zero, and I learned in science classes that that was the temperature at which all motion stopped. Turns out that's not correct. And we've known that for well over 100 years now. And since the development of quantum mechanics, we found out that even at absolute zero, there will be energy in a system, but there isn't, everything would be in its lowest energy level. And this is a quantum mechanical thing, but that lowest energy level isn't zero, and motion hasn't completely stopped. It's just a state that you can't take any more energy out of. So now there's also this thing called the Kelvin scale. And for the Kelvin scale, 0 is where an ideal gas would exert no pressure. And some of the things we're going to study will be interested in stuff that happens. And some of those things don't happen at 0 Kelvin, but as you go up, then the amount of stuff that it is, like pressure exerted by a gas, increases linearly with temperature. And on the Kelvin scale, the symbol for the unit is just a capital K, and it's written out as a unit with a lowercase k. And there is no degree on the Celsius scale. You just call it 0 Kelvin. Or if you're up here, this would be 273. Now I'll write all those sig figs. 0.13 Kelvin. And if you've got a bunch of Kelvin, you can call them kelvins with an S on the end if you want to. And then water boils at 373.15 Kelvin. And just sticking an uppercase K there signifies that you're on the Kelvin scale. Now, you may notice something. It's 100 degrees Celsius from where water boils to where water freezes. It's exactly 100 Kelvin from where water boils to water freezes. And so the step size, as far as a delta temperature goes, you can say that if you have a delta T of 1 degree Celsius, you also have a delta T of 1 Kelvin. And so the step size is the same. And a lot of the things we study, we're going to be interested in the change in temperature. And so we can use Celsius or Kelvin for that. In fact, a lot of times you'll be given one or the other. And those are things that we'll talk about. Now, the chapter that we're starting here is chapter 17. And this is discussed in one of the earliest sections in there. I suspect if you've had a chemistry class, you've probably dealt with both of these temperature scales before. And again, I'm just not going to mess with Fahrenheit at all. I used to, when we lived in Moses Lake, we would often have the National Public Radio station out of Pullman on the radio in the morning, and they'd be reading off the temperatures, and they'd say something like, oh, the temperature in Moses Lake is 28, and temperature in Wenatchee is 27, and the temperature in Penticton is -4. And then they'd go on and they wouldn't tell what the units were. Well, it turns out Penticton is in British Columbia and they use the Celsius temperature scale up there. And so a temperature in the 20s Fahrenheit wise would be -0 on the Celsius scale. My father-in-law grew up in Lebanon and was comfortable with the Celsius scale. He lived in the United States long enough that he got comfortable with the Fahrenheit scale as well. But my wife and I lived in Minnesota when I was in graduate school, and she was talking to her father one time on the phone, and he asked how the weather was, and she said, "Oh, it's pretty cold. It's getting down to 10 below tonight." And he said, "They use the Celsius scale in Minnesota?" And she said, "No, that's Fahrenheit." And he'd lived in Seattle ever since he immigrated to the United States, or for nearly all of the time since he immigrated. And in Seattle, they had never had a temperature below 0 on the Fahrenheit scale. And so he just couldn't conceive of a temperature that cold. But it can happen anyway. All right, enough about temperature scales. One of the very first things we're going to look at having to do with temperature changes is thermal expansion. And this is something that happens with most materials. And that's what we'll do some calculations with this today. Whoops. And for many materials, when you change their temperature by having a raise in temperature over a fairly large range, they'll expand. And we'll start considering by linear thermal expansion. So if you've got say a piece of rebar or something, iron or steel or something like that, that's some particular length, and you heat it to a higher temperature, or today, I don't know what the temperature is outside, it's in the 40s somewhere. But if I've got some pieces of rebar sitting around, if I took those rebars and measured their length today with a tape measure that didn't change length with temperature, and then did the same thing in the summer on a day when it's 60 degrees Fahrenheit warmer, I'd find that those things are longer and that they expand. And if I had a short piece of rebar and measured its increase in length, I found out that it's not as great an increase in length as for a long piece of metal when I increase its length. So that's something that happens with a change in temperature. Well, here's the way we express that. We'll talk about a change in length, delta L. It ends up being proportional to the length that we actually have. And so that might be the length before the temperature changes. And you're going to have to be careful with these things because it'll be the length at a particular temperature, maybe your starting temperature. So delta L could equal L final minus L initial, and it'll be proportional to the length. And I'm leaving a space here because I'm going to fill in something. And then the change in length will be proportional to the change in temperature as well. And proportionality constant, alpha, is what we use. We call that the coefficient of thermal expansion, and it depends on what the material happens to be. Some things expand more than others. Maybe, I think next Tuesday probably. Well, let's see, we're having a test. I may still show some demonstrations of things that happen with thermal expansion, and we can become a little bit familiar with that. But we could think of this as alpha L times T final minus T initial. So we'll have that going on. Anyway, a lot of times we just write it as delta T and don't worry about it all that much. But L final would be the length at whatever T final happens to be, and L initial would be the length at whatever T initial happens to be. And you sometimes have to be kind of careful with these. Okay, here are some coefficients of thermal expansion. And these are for various materials. You can ignore this column because it's for degrees Fahrenheit, and we're just not going to care about that. But it's got ordinary glass. Now, something to notice up here, these are small changes, times 10 to the minus 6 for all of these things. So ordinary glass will expand by 9 parts per million per degree Celsius. By the way, we can change this formula so we have a delta L over L. This would be a fractional increase in length, and that'll equal alpha delta T. Okay. So that way you'd have the fractional change in length, and then you'd be taking the coefficient of thermal expansion and multiplying it by a delta T. So I'm not sure just where I happen to get these three, but it starts with ordinary glass, then goes to Pyrex, and then goes to fused quartz. Okay, Pyrex is the glass that used to be. It was borosilicate glass, and I guess somebody bought the license for using that word Pyrex, and now it doesn't necessarily mean it's such good glass anymore and that it works that well. But ordinary glass, if you had something like say a glass cake pan or something like that, and you exposed it to a sudden change in temperature, like for instance, if you had it having something hot in it and then you poured some ice water into it, or vice versa. Let's see, I can remember having a cold glass once and pouring some boiling water into it to make tea or something. I don't remember. And it shattered. Glass does that because it makes rapid changes. Pyrex, on the other hand, has only about half the coefficient of thermal expansion of glass, and so it's more resistant to those sudden changes in temperature. It's less likely to do it. Quartz, and quartz is a very glass-like substance when you have it. Looks kind of like glass if it's melted, and it'll make nice smooth things. It's got a very small coefficient of thermal expansion. Used to be, people would make their telescope mirrors out of glass. Actually, it isn't the mirror, it's the thing that you grind into the shape of a mirror, and then you put a silvering substance on it, and they'd make it out of ordinary glass. And it had a problem where in the evening, say if you'd had your telescope sitting outside all day, the temperature drops quite a bit in the surrounding air, and so the telescope mirror would be changing temperature gradually. And if it was a telescope mirror built on a glass form, it would take, well, it'd have some fairly major changes in shape to undergo. And while it's doing that, it doesn't provide sharp images. Pyrex was a preferred material for them because they didn't have such huge shapes. But nowadays, you can buy quartz blanks to make reflecting mirrors out of, and those are way better. And the prices of them weren't astronomical, I guess. They weren't horrible compared to the cost of a Pyrex one either. So you have that going on. Okay, and then we start looking at some metals, and metals expand and contract much more than the glass does. So usually you don't have to worry about those things too much. But I need to send a text down here. tell my wife to stop trying to do amazing things with the dog. Anyway, a bunch of different coefficients of thermal expansion. And we'll do probably a last lab this quarter, or one of the last labs we'll do will be one where we measure the coefficients of thermal expansion for, I think, aluminum, brass, copper, and steel. I don't have any platinum rods. If I did, I could probably sell a single platinum rod and make about as much money as I'd make for 3 classes or something like that anyway. And I don't have gold or silver rods, but at any rate, here's a bunch of different things. You can see tungsten has a pretty low coefficient of thermal expansion, at least as far as these metals go. But still, it's parts per million that show up on these things. So let's try a few examples. And these can be relatively simple problems, but they can also get complicated. It used to be when they did railroad rails and laid them out, they would leave a gap between the rails. And so if they laid them when the temperature was cold, and this is one rail, they'd leave a gap between them, and the gap depended on what they expected the length of the rail to be at the highest temperature. And what they do is look at temperature records and find out, okay, they've actually had temperatures of 115 degrees here. We need to leave a fairly large gap. And when you were riding on a train on those kinds of rails, when the wheels happened to come to these expansion joints, you'd hear this kind of chunka every time the wheels rolled over one of those things. And it just became a familiar sound when you were riding on a train, this sort of periodic chunka, chunka, chunka. And the faster the train was going, the more frequently you would hear that kind of just a sort of little thump that transmitted through there. Nowadays, they use continuously welded rail. And so they'll start with very long sections of rail, and then as they're laying them, they'll weld adjacent lengths of rail together. And they would still want to expand, but they fasten them down much more thoroughly nowadays than they used to. And so there's a video on YouTube where a guy investigates the thermal expansion stuff. And then there's another number related to how much stress the rail can undergo before it expands. And it's a more complicated thing. But anyway, this problem's back in the old-fashioned days. They lay them when the temperature is 0 degrees Celsius. What gap should be left between rail sections so that they just touch when the temperature rises to 42 degrees Celsius? And the sections are 12 meters long. And for steel, we're going to use alpha is 11 times 10 to the minus 6 per degree Celsius. Well, the delta L is going to equal alpha L delta T, and we've got everything we need here. This is a pretty simple one. Alpha is 11 times 10 to the minus 6 per degree Celsius. Per degree Celsius. L is 12 meters. And the delta T, it's going from 0 degrees up to 42 degrees Celsius. This would be the final temperature. So 42 degrees Celsius is what that happens to be. And it's just a fairly simple multiplication problem. This is as easy as a thermal expansion problem could get, actually. But And I would get delta L of 5, actually, I'll just round it to 6, times 10 to the minus third unit-wise. These degrees Celsius will divide out with those, and we'll be left with meters. And that's 6 millimeters. Actually, kind of looks like we've got 2 sig figs, so I guess we could write this as 5.5. That would work out okay. Keeping 2 significant figures, but it might be safest to leave 6 millimeters just to have that. Now, that's not all that big a gap. So wherever 6 millimeters is, but it's a little bit of a little bit there. So a little bit of a change. All sorts of things have to be built in a way that will allow for thermal expansion. You'll sometimes see on a metal bridge, and usually I'm driving at freeway speeds as I'm going over the things, but I was just thinking of the bridge across the Columbia River at Vantage. They probably have some kind of expansion joints on there, but they don't do them where it's just a linear thing. What they'll do on bridges like that is they'll have the part that's attached to the land on either side, and then they'll have the part that's on the bridge, and it's kind of floating, not exactly attached to that part that's on land, but there'll be some things like this where there's a bunch of metal fingers, and these things might go all the way across the roadway, and then there would be metal fingers in the opposite direction doing something like this for the other part of the bridge. And when the temperature is very high, these things might almost meet at the end of the thing. And when the temperature drops down, they start to have a separation. But because of these interlocking fingers, they don't ever end up with a huge gap on the thing. So that's a way that they deal with them sometimes. Okay, now we'll do a few problems with linear expansion, but this is one looking at the area A of a rectangular plate is AB. Its coefficient of linear expansion is A. After a temperature rise of delta T, what will its area be? Well, this is going to be kind of interesting, but let's just go ahead and draw our little rectangular plate here, and I'm going to kind of continue that a little bit. Okay, and this can be A right here up to that point. And then this could be B here. And this is going to be an approximation that we're going to learn about here. That looks pretty parallel. Didn't quite do it long enough, but good enough. Okay, so here's the original area that we have here. It's some original T, and the area is going to be AB, just length times width or whatever you want it to be. But now let's imagine what's going to happen when we raise the temperature of this. Well, it turns out all of the dimensions increase by our thermal expansion thing with a linear expansion coefficient. And so the dimension in this direction ends up increasing by a little bit. And so we'll have something here. And this amount here is going to equal, I can think of it as delta B, which is going to be alpha B delta t. So that'll be part of it. And then this part up here is going to have a similar change in length. Where this little thing right here is going to be delta A, delta lowercase a, which is going to equal delta lowercase a is going to equal alpha times a times delta t. And then there'll be some little tiny square here that we'll talk about the area of that. Well, what about the change in area? The change in area, delta capital A, there'll be a delta A times B. There'll be a delta B times A. And let's see, I'll also have plus delta B times delta A. Okay, and that'll be this little thing here. Delta B times delta A. Okay. Well, I know what delta A looks like. It looks like alpha A delta T. This looks like alpha B delta T. So our change in area will equal alpha A delta T times B plus delta B, delta B is equal to alpha B delta T times A. And then here I'll have alpha A delta T times, that's a plus sign there, times alpha B delta T. Yeah, and that's what I'll have. Well, this thing actually ends up looking an awful lot like this thing. In fact, if I reorder the terms, they both have an alpha, they both have an A and a B, and they both have a delta T. So I actually end up here, these two add together and give me 2 alpha, oops, I didn't need an alpha there, 2 alpha AB delta T. That's what those add together. So this is delta A is going to equal this. And at the tail end, I'll have alpha squared AB delta T squared. Okay. And so remember how small alpha was? It was maybe, I think for aluminum was one of the largest ones, and I can't remember where I got those showing. Yeah, aluminum had the highest one on here, 24 parts per million. Okay. If you square that, and I'll just square 24 parts per million, I would get like 5.76 times 10 to the minus 10th. Okay, that's at least, let's see, it's actually going to be about 5 orders of magnitude, or 1/100,000th of this amount here. And we just ignore this because it's so small compared to this. And coefficients of thermal expansion are typically only known to maybe 2 significant figures at best. And so trying to go 5 decimal places past this term just isn't going to be noticeable. And so what we end up with is that the change in area ends up equaling 2 times the linear coefficient times the area times delta t. So if you know the linear coefficient of thermal expansion, the area coefficient is just twice that. And so that's something that happens. And that'll be the new area. What will its area be? The final area, A final, is going to equal A plus delta A, which is going to be, let's see, AB plus 2 alpha AB delta T, and you can rewrite this as AB, the original area, times 1 plus, we don't usually bother to figure this out, but it'll be 2 alpha delta T. And the big idea out of this one, though, is an area coefficient of thermal expansion will be twice that of the linear coefficient of thermal expansion. So that's a big idea here on that one. I don't have any, well, I think the book has, I don't know if you'll be able to see this at all, but the book has a table in there for coefficients of volume expansion. And if you look at things like aluminum, the coefficient of volume expansion is 3 times as much as the linear expansion. The same with brass, copper, all these various things. You just take the linear coefficient of thermal expansion and multiply it by 3 to get the volume coefficient of expansion. So that's something that comes out of this stuff. Okay, let's do one that's more complicated here. We have a steel sleeve that has an inner diameter of 1.000 centimeters at 25 degrees Celsius. A solid copper rod has a diameter of 1.001 centimeters at 25 degrees Celsius. To shrink fit the two together, the steel sleeve is heated. Okay, that'll make the inner diameter of the steel sleeve increase in size, and the copper rod, let's see, oh, all we're doing is heating the steel sleeve in this case. And we'll try to figure that out. So we can think of this as, oh, it doesn't actually say what's going to happen in this thing. But then we're going to put it in a very cold environment. And at what temperature will they separate? Now, in a very cold environment, the steel sleeve with a hole in it is going to get smaller, and the solid copper rod is going to get smaller, but there's a difference between coefficients of thermal expansion for steel and copper. And so at some point, let's see, the copper is going to shrink more as the temperature decreases than the steel does. And at some point, the copper will be the same size as the steel. And at that point, they'd probably separate. So let's see how this might work out. We'll start with the steel. The new diameter of it. D final will equal the D initial for steel plus alpha D initial for steel. This is kind of complicated, times delta T. Now we're going to have a negative delta T. We're going to drop the temperature down from 25 degrees Celsius and take it down there. And then we've also got the copper sleeve. And I want the final diameter of the copper sleeve to be the same as that of the steel. So I'd have a diameter initial for the copper. I'll use Cu for copper. Plus, whoops, I need to designate that I'm using the coefficient of thermal expansion for steel here and the coefficient of thermal expansion for copper here. So D initial Cu times delta T. Okay, so it's a pretty complicated expression here, but delta T is going to have to be the same if these two, well, if they're in the same environment, you're putting the two in a very cold environment. At what temperature will they separate? Well, let's do a little bit of algebra and solve for delta T. Let's see, I'd have, which one's bigger to start with? The copper is bigger. So if I bring these over to here, Cu minus Di for steel, that's the initial temperature. And then I think I'll take the delta T's to the other side. So I'd have alpha for steel, D initial for steel, delta T minus alpha for copper, D initial for copper, delta T, capital T. Factor out the delta T. And that's going to equal this difference right here. Now, one thing about this problem here, this difference here is going to be 1.001 minus 1.000. We're going to be down to one significant figure here unless I can figure out some clever way of dealing with this. But, oh, that's not a separate variable. That's a subscript. Anyway, the delta T, which is going to be T final minus T initial, is going to equal, I'll just divide by that, and it's going to be some kind of ugly math. Alpha for steel, the initial for steel minus alpha for copper, the initial for copper. And I would expect that this is going to be a positive numerator. I'd expect to have a negative denominator here because I expect the temperature difference to be negative. And T initial is 25 degrees Celsius. T final should be some amount less than that. But let's plug in numbers and see what we get here. Sometimes these mixture problems of sorts are kind of complicated. Anyway, I'd have the copper 1.001 centimeters minus 1.000 centimeters. I can do that one in my head. But this one down here is going to be kind of complicated. I think I'll slip another piece of paper under here. Just so I can finish off the calculation. Alpha for steel. Oops, that's one I had to look up again. It is 13 parts per million. So per degree Celsius times the diameter of the steel, which is 1.000 centimeters, minus for copper it's 17 parts per million. Times 1.001 centimeters. Okay, well, nothing left to do but just plug in numbers and see what we get. And remember, we've only got one significant figure up here, so we're not going to be able to um, do a whole lot with this, but I get a delta T of about, um, is that right? Maybe it's right. Let's see, unit-wise, the centimeters will divide out. I'll end up with degrees Celsius on this. Well, it does say very cold. I get a delta T of about minus 250 if I didn't make a mistake. So T final is going to be T initial minus 250 degrees Celsius, but I'm pretty sure I punched it into my calculator right. This would actually be 13 parts per million. This would actually end up being about minus 17, so it'd be 4 parts per million. Yeah, that makes sense. Okay, anyway, it'd be minus 225 degrees Celsius. That's maybe pushing it a bit, claiming keeping two significant figures on that because we just don't have that much precision. It might be better to think of this as 200 degrees Celsius, dropping off of that initial temperature of 25 degrees Celsius. But at any rate, that's about what it is. I was to rewrite this problem, I'd add another significant figure on each one of these things and also make so they weren't, one of them wasn't exactly 1.00 centimeters. That might be more interesting. Anyway, there's one of our complicated problems. Here's one that has to do with a volume change. And imagine an aluminum cup of a 100 centimeter cubed capacity filled with glycerin at 22 degrees Celsius. So it's filled. That means the glycerin is even with the top of the aluminum cup. How much glycerin, if any, will spill out of the cup if the temperature of the cup and glycerin is raised to 28 degrees Celsius? Well, we can use volume coefficients of thermal expansion for this. Actually, I do have the volume coefficient of thermal expansion for glycerin here. For helium, and by the way, we use beta, Greek letter beta, for volume coefficients of expansion. So I'd use beta sub GL being that. Beta for aluminum is going to be 3 times alpha for aluminum. And alpha for aluminum was 24 times 10 to the minus 6. Multiply that by 3 and you get 72 times 10 to the minus 6 for alpha for aluminum. So okay, so we've got each of those things. Now this one is 5.1 times 10 to the minus 4th, which would be 510 times 10 to the minus 6. So glycerin's going to expand a lot more than the aluminum is. So, all right, well, I guess I can just do V final for the glycerin is going to equal V initial for the glycerin plus beta this time, V initial for the glycerin times delta T. Delta T is not that much in this case. It's only 6 degrees Celsius warmer. And then V final for the aluminum is going to equal V initial for the aluminum plus, whoops, this is beta for the glycerin, plus beta for the aluminum, V initial for the aluminum, delta T. And to save calculation stuff, I'd have V initial for the glycerin times 1 plus beta for the glycerin, delta T. And this will be V initial for the aluminum. And to start with, the volume of these things, the aluminum is 100 centimeters cubed, so is the glycerin. So it all boils down to these coefficients of thermal expansion. Okay, well, this will be 100 times beta sub GL is 5.1 times 10 to the minus fourth times 6. This will be 100.3 centimeters cubed. When I multiply beta times a delta T, the units go away on it. And for the aluminum, let's see, we have whoops, forgot, put a wrong sign or wrong thing in there. 72. Oh, I got a syntax error. I must have screwed up somewhere. Try this again. Oh, there we go. Okay, so for the aluminum, it doesn't change much in volume with that small a thing. It's essentially still 1.000. And it looks to me like if I subtract this one from this one, I'll end up with about, we've only got one significant figure on the temperature change. So I'll be down to 1 sig fig on this, but it'll be about the spillage is going to equal V final for the glycerin minus V final for the aluminum. And it's going to be this minus this, and it's actually 0.3 centimeters cubed, or 0.26 if you, oh, I forgot, that's times 100. That decimal point is over there. So anyway, not a whole lot, but that's a volume change one. Let's see if we had this one. would take longer to do than we have left, but I may save this one for maybe Monday or something like that. But, or you could try it for a practice problem. I'll have these things posted. We have a rod that's exactly 20.05 centimeters long. Well, maybe. Using a steel ruler at room temperature of 20 degrees Celsius. And then both the rod and the ruler are placed in an oven at 270 degrees Celsius, where the rod now measures 20.11 centimeters using the same ruler. And we want to know what's the coefficient of thermal expansion for the material of which the rod is made. This one's complicated. It's kind of an algebra challenge to set this thing up correctly, but we'll save that for another day, or you can give it a shot if you want. Actually, this may be on a homework assignment, so it's a good thing I'm not doing it. I'm not sure. But there's a little bit of an introduction into thermal expansion and things like that. At school, the experiment we do where we determine those things, we have a hollow aluminum tube that you put the rods in, and we measure their lengths using a kind of a, well, we screw something down onto it and make it somewhat snug, but the device that we screw down onto it has the ability to measure the change in length of the rod to within to 1/100th of a millimeter. And so we can measure the lengths of those rods before we even put them in the thing, and then put them into the thing, expose them to steam, get their temperature up to as close to 100 degrees Celsius as we can, and then we see what the change in length is. And so we'll be determining the alpha L pretty carefully, and for the delta L, delta L, and that'll equal alpha L delta T. Well, we're measuring delta T, we can measure L, and we can measure delta L. So alpha will end up equaling delta L over L delta T. And because we can measure this to within 1/100th of a millimeter, even though maybe we don't measure the length all that precisely, we can measure it to certainly 2 significant figures. And the temperature, we can also measure to 2 significant figures. So we can end up with a value for alpha of 2 significant figures anyway. And that's the way we'll do it. It's kind of a messy lab because we've got steam being routed through these things through rubber tubes, and then we have to drain the metal tube that the steam is poured into, and so we'll have tubs underneath the tables for doing all this stuff. It's kind of messy, but it works. Okay, tomorrow sometime noonish, I think, maybe a little bit afternoon, I can't remember. I hope to have a review session for the test, and before then I should have the first optics homework graded for you, and I'll also have a formula sheet ready. The formula sheet's about halfway done so far, and I haven't had time to work on it today, but anyway, I'll make those available. And I posted or gave you a link and an announcement to the video for the test or the homework 6 question and answer session last night. So that should be available to you as well. Anyway, I'll stop the recording and